screens here. You're probably watching me. I'm just making sure the screens are working so that this is working. And it takes a little bit because we're on a delay. Also going to find my paint feature. Oh, there I am. Must be working. Sorry, I'm a little late. The little girl did not want to go to sleep. Okay. All right. Okay, looking at the questions, I only have 6 questions, so we'll just start at the top and work our way down and see how we do. What is molarity, and what does something with a high molarity look like? What does something with a low molarity look like? Okay, so I'm going to go to my split screen. There's something in my eye. I'll make it. I'll show you my screen. Yes, this is what I want. Okay. I believe you can see my screen now. Okay, so molarity is technically defined as the moles per liter. So it's technically the moles of the solute divided by the liters of the entire solution. So what molarity kind of tells you is like how much stuff is packed in, and that's what I'm going to kind of talk about the next question, which is what's something with a high molarity and what's an example of something with a low molarity? I think it's a sort of question like that. Pull it back up. Okay, what does something look like with a high molarity and what does something look like with a low molarity? Okay, so when you think about concentration, which is what molarity is, it kind of makes me think about how much stuff is packed into an area. So another way to do concentration would be like parts per million or parts per trillion, if you've heard that before in real life. But molarity gives you like real values. So let's say you've got a box, and this is a Kleenex box. And you just opened the box of Kleenex. So it's completely full with Kleenex. And if it's completely filled with Kleenex, it would have a high molarity. Big M for molarity. But once you take a couple Kleenexes out and you use them, then you now have less stuff packed in. And if you have less stuff packed in, then it's a lower molarity. You've just suddenly lowered the molarity. So that would be an example of something with a high molarity and a low molarity. Another example of a high molarity would be something like laundry detergent. So something, here's my laundry detergent, like a liquid laundry detergent. It's a lot of stuff packed in. But what you'll do is you'll dump that laundry detergent into your big tub and you'll fill it up with water. And when you fill it up with water to the top, now you've just diluted it. And so you've got less active ingredient inside that container. With less active ingredient, it's kind of like basically you're saying you have less moles. If you have less moles, less active ingredient, you have a lower molarity. I hope those two make sense. My 2 examples. Okay. Yeah, that's my. Here's my mouse. Okay, my next question is, in the mole map, why do atoms and ions are in 2 boxes? There's a big box and a small box. So when converting from molecules to atoms, do I need to multiply the molecule by the number of atoms? Okay, we'll do some practice problems with that. So yes, there are 2 boxes. Draw myself a little mole map right here. Here's your grams, moles, liters. This top box has atoms, ions, formula units, and molecules. And over here we got atoms and ions. Okay, so let's say you had a problem that asked you, how many atoms do you have when you have 6.3 moles of Fe2O3? And then another question you could have is, how many atoms do you have when you've got 2.2 moles of Fe? And then a question would be, how many ions do you have when you have 6.1 moles of Fe2O3. Okay, so these would be my 3 different problems here. We'll start with the first one. How many atoms do you have when you have 6.3 moles of Fe2O3? So in that case, when I look at Fe2O3, I need to ask myself, as I go up from moles into this upper box here, what kind of substance is Fe2O3? Is it an atom, an ion, a formula unit, or molecule? Well, I would say Fe2O3 is a formula unit. So I will go from moles on the bottom to get them to cancel to formula units on top, because as I go to the top, I would call it a formula unit, so that's where I'd go. I know 1 mole would be equal to, the conversion factor in that case is the big number, 6.022 times 10 to the 23rd. I am tight on space here, sorry. And then I'm going to multiply it by another fraction, I'll do it down here, in which I want to get out of faux U's and into atoms, because that's my whole goal here. So I'm going to take that faux U side step to atoms. In this case, I would say 1 faux U, formula unit. Basically, formula unit means 1 ionic compound, 1 Fe2O3, has 2 irons and 3 oxygens. That's a total of 5 atoms. 1 formula unit makes 5 atoms. My faux U's cancel, and I'm left with atoms, which is totally what I want. Just bust out my calculator at this point and come up with a number. This is different from the next question, which is asking about atoms when I have iron. So I'm going to get out of moles, put that on the bottom, and then once again I'm going to head up to the top here, and I would ask myself, if you just have Fe, what would you call it? Well, I would call it an atom. So in this case, I can just do one step. I'm going to go straight from moles to atoms, because Fe is called an atom. In this case, 1 mole equals 6.022 times 10 to the 23rd atoms. And that would get me to the end, because I want to know atoms. And this is yet again different than my last case here about ions. So at the bottom here, I'm going to put moles to get rid of them. Look at my substance, Fe2O3. So as I'm headed to the top, I ask myself, what is Fe2O3? Well, it's a formula unit, because it's a compound, an ionic compound. So I've got to go to formula units on top. 1 mole, 6.022 times 10 to the 23rd formula units. And then I'm going to multiply by faux U's on the bottom. That way I can get rid of them, formula units. I'm going to go across to ions. So in this case, I'm going to go to ions. And ions here would be, I have 2 iron ions and 3 oxygen ions, which gives me a total of 5. It'd be a 5 ions to 1 faux U, once again. But this isn't always the case. It's not always the same as atoms. Like, let's change it to a substance like FeOH3. If I look at the total number of atoms in this case, in this guy, he's got 1 iron, 3 oxygen, and 3 hydrogen. That makes a total of 7 atoms. But in this case here, he has a total of 1 iron, 3 hydroxides, 4 ions. So you can see that atoms and ions aren't always the same thing. They can be a little bit different depending on what kind of compound you have. Okay, so I think that answered that. I didn't mark down the time. I guess 8:30. Okay, number 4. Is limiting reagent the same as limiting reactant? Yes, they mean the same thing. So yes, they mean the same thing. When calculating percent yield, is the unit percent? Yes. Well, those 2 questions were pretty easy. I'm going to give you a few moments to see my video because you're on delay. And then we'll see if there are any more questions. If there's not, we might just call it a night here. sent me an email. Mm-hmm. Okay. I think with that, I might call it a day. I don't see any other questions. I see people on there, so that's great. I guess if you have any personal questions, just send me an email and I'll shoot you an email back with the answer. Right before I go to bed, I'll check. And you should go to bed, people. Go to bed. And then I'll check in the morning when I get up too. All right, good luck. You'll do great. Have a good night.